Okay, thank you very much, Egan. Hello, everyone, and thank you for attending this webinar today. In my presentation, I'm going to be starting out by outlining some of the challenges of designing heavy equipment, particularly when it comes to the handling of bulk materials. I'll then move on to explaining how a coupling between our software EDEM and Adams can provide additional insight into understanding heavy equipment performance. I'll follow this then by showing you a little bit of detail around the workflow and then also some industrial examples. So at the end of the talk, as Egan says, there'll be an opportunity for a Q&A, so please feel free to ask any questions if I don't cover the information during the slides. Okay, so engineers, when they're designing heavy equipment, are challenged on a daily basis by the complex nature of the material that their machines will face. So when in operation, nearly every aspect of a piece of equipment's performance, from the stresses on a load arm to hydraulic forces to perhaps even the traction of the tires and delivery of power, is dependent to some degree on the bulk material being handled. And when I say bulk material, I really mean things like clays, soils, mine doors, gravel, or even just rocks. But understanding how a design is going to perform in a particular material environment is really critical to ensuring an optimal design that combines strength and durability with performance efficiency. So some examples of important optimizations in the heavy equipment sector include things like the reduction of weight of equipment, increasing fill levels, and reducing loading and unloading cycles. Now, real bulk materials are complex in their behavior. Across a range of different materials, you can see variations such as quite a wide difference in things like shape and size of the individual particles that make up that material. For some materials, say for example sand, moisture can also play a huge role. And on one day it can be dry and free flowing, but after a heavy rain shower, it becomes highly cohesive and very difficult to handle. Now, the variability and complex nature of materials means that it's very difficult for engineers to predict exactly how they're going to behave when they're designing their heavy equipment. Systems dynamics tools, such as Adams, are commonly used in the design of heavy equipment, and here an engineer really has to tackle the problem of material loads head on. So traditionally, in order to get such load data for use in their analysis, engineers need to use hand calculations or assumptions of the material behavior to try and predict the forces and torques that a bulk material will have on their particular design. Now, because of the complexity of predicting material behavior using such methods, an engineer may only be able to assess a small set of corner case conditions, such as, for example, the estimated maximum load at one point during a particular operation. Now, an alternative approach is to integrate the systems dynamics software with a physical test where experimental data is then integrated into the simulation to produce more accurate and realistic loads to represent that complex bulk material. However, experiments can be costly and time-consuming in order to set up, and typically, because of the constraints of time and the costs associated, they're really restricted to only a small number of materials that are available and predefined motions. So obviously as well, if you're performing experiments, you have to actually build the design you're interested in testing also. So faced with these challenges, how then can an engineer get accurate loads for a range of material types and behaviors, and also evaluate those designs under a wide sweep of equipment usage conditions? At EDEM, we are the market leaders in providing commercial discrete element modeling, or DEM, software to address challenges related to real-world bulk material behavior. For those of you not familiar with DEM, it is a method where a bulk material behavior is recreated in a virtual environment by modeling hundreds of thousands, if not millions, of individual material elements called particles. EDEM is an easy-to-use and powerful simulation tool that provides engineers with the ability to create realistic material behaviors for a wide range of different material types. It provides a range of analysis tools required to solve complex problems in the design and optimization of bulk materials handling and processing equipment. EDEM is used across a range of different industries, in particular by companies in the mining and construction sectors. By introducing EDEM simulation analysis into their design workflow, equipment manufacturers are able to significantly reduce their reliance on things like assumption and physical prototyping, and can increase the productivity and reliability of their equipment by understanding exactly how a material will affect their designs throughout the design cycle. So, for example, here in the top right, we have an example from a company called WesTech. Now, WesTech have used EDEM to design the world's largest truck body that combines strength and durability with an increased payload and reduced unloading time. On the bottom left is an example from a company called VR Steel. VR Steel design and manufacture some of the world's largest surface mining equipment and have used EDEM to reduce operational costs and maximize loading efficiency with their dragline buckets. And finally, Hatch Associates. They use EDEM technology to help improve the transfer of coal and other mine products as they are moved from point to point in mining operations. Here, EDEM allows them to ensure the performance capacity is maintained of a plant and that transfer points are safe and robust during usage. As noted previously, materials can come in an endless range of sizes, shapes, and properties. So you could be dealing with heavy-duty, large quarry rocks that are generating high-force impacts, or perhaps fine but highly abrasive materials such as sand, or even cohesive clay-like materials that can be difficult to handle and stick to equipment. Each of these material types can be simulated within EDEM. In the video on the top left, we have a large lump material which shows the path of the bucket as it moves through the rocks. In the video on the bottom, we have an example of a cohesive material, and here you can see how the material sticks together within the bucket, and it shows a significantly greater fill level than that of the rocky material. And then finally on the top right, we have an example of a very fine, very dry material, so like a free-flowing sand. And as you can see by the behavior of the material as it interacts with the bucket, this material is much more free-flowing and is spilling over the sides of the bucket in a way that's not seen in, for example, the cohesive example. Now, the different attributes of a material will influence the design of your equipment. And of course, there are not just 3 different types of materials out there. If you consider a mining operation, your equipment may need to deal with 3 or more variants of iron ore, for example, from a single location over a short period of time. Material properties and behavior could vary from season to season, so from summer to winter as the moisture content varies. And then when you extend this to dealing with different locations around the world and different material types, there's a huge range of material conditions that your equipment is likely to face. EDEM provides engineers with the ability to model this wide range of material behavior, from the coarse dry rocks to the fine cohesive powder, as well as dealing with a mixture of different material types. Driven by the material challenges faced by engineers, MSc and ourselves at EDEM have worked together to develop an Adams-EDEM co-simulation capability that will be available in the upcoming Adams 2016 release. The overall premise is pretty simple. So when you're performing a co-simulation using the coupling, both EDEM and Adams run simultaneously. And during processing, there is an exchange of data between the 2 software. On the EDEM side, we gather all the material load information that is acting on the equipment over time. This information is then passed to the Adams solver, which then uses the load data to understand what impact this will have on the equipment motion, and then provide an update to the position of each of the components. This change in equipment position is then passed back to EDEM, where the geometry on that side is updated. This process happens repeatedly throughout the simulation and results in a realistic force feedback mechanism on the equipment until the overall simulation cycle is complete. This co-simulation solution that combines the material modeling benefits of EDEM and the power of Adams systems dynamics analysis allows a 100% computer-aided engineering approach to design. It allows engineers to quickly and easily use realistic material loads in their analysis of heavy equipment and minimizes the reliance on the traditional hand calculations and assumptions in their design process. By linking together EDEM and Adams, engineers can predict and understand the effect of material flows and loading patterns routinely as part of their design process, and give themselves the freedom to repeatedly test the performance of their equipment under a range of different field conditions before moving on to fabrication. It does not require any field test data to operate, and by using EDEM, a wide range of material types and flow behaviors can be looked at. This means that equipment can be designed in such a way that it delivers improved efficiency and performance, as well as ensuring safe structural design. Next, I'd like to just go into a bit more detail and talk you through the workflow for the Adams-EDEM coupling. So, engineers can start out by setting up their EDEM simulation. Now, for those of you who have not used EDEM before, there are two key aspects to this. One is to import your equipment design into the software, and EDEM will allow you to import a range of standard CAD formats. Once there, you're able to define either a series of simple dynamics in the software, or obviously then subsequently link it to Adams itself. The second part of the process involves defining the material that your equipment will interact with. Now, definition of a suitable material is key to a successful DEM simulation and requires definition of a number of different parameters that control the behavior. This includes things like the particle shape and size, the physics models that will ultimately dictate how that material is going to behave. For example, you can add in models that represent the sticky effects of moisture, and then also the parameter values that feed into that physics model to control exactly how that behavior is going to be calculated. So these are typically things like friction or restitution coefficients. Now, traditionally, this would require someone with a reasonable degree of DEM experience, which is great if you have it. However, at EDEM, we recognize that not everyone has such a resource readily available. And so to make material modeling more accessible to a wider engineering audience, we've developed a world's first, the GEM database. This is a database that contains over 10,000 fit-for-purpose material models. Accessing the GEM is free and is available free on our website at www.edemsimulation.com. Engineers simply go to our website and enter three pieces of information about their real materials. So the bulk density, the approximate size of their application, and then an angle of repose. And based on those three bits of information, they're instantly provided with all the inputs they need, including things like particle shape and size distribution and all the physics parameters that are required to reproduce that material behavior within EDEM. So, with the material set up and the equipment ready to go, the EDEM part is complete. The next step is the user setting up their Adams simulation by bringing in again the required geometry components and defining the required physics as per usual. Once both simulations have been set up, the user is able to connect the two together using the Adams Cosimulation interface, the ACSI. Dejan said, the ACSI was introduced into Adams about 2 years ago and is a general purpose co-simulation platform that enables Adams to be linked with other codes. Setting up the connection required between Adams and EDEM involves the definition of a configuration file that allows data to be transferred between the different geometry parts in the two different software packages. So, to assist the setup process, the ACSI provides a graphical user interface to allow the configuration file to be created. The connection between Adams and EDEM is based on G-force markers, and these are linked to EDEM geometry within the configuration file. By forming these links, Adam is able to drive the system dynamics and will react accordingly to the EDEM material forces acting on those parts that have been linked. Users are free to link as many parts as you need to perform the co-simulation, whether that be just a single part that's going to be directly interacting with the material or the whole equipment assembly itself. Now, the benefits of using the ACSI include the users not having to write their own coupling code. So it's simply the case of defining this configuration file. In addition, EDEM and Adams solvers can be set up to run on different machines. And there is full flexibility to set up the simulation on each side using the standard units and orientations that you would use normally without having to use exactly the same inputs on the EDEM and the Adams side. And then obviously, finally, by enabling the co-simulation, the ACSI allows users to increase the accuracy of their overall system simulation. Just as an aside, the ACSI was originally developed to allow Adams to connect to Mark. Now, by developing the EDEM coupling using this same interface, it's now possible to also perform a three-way simulation between EDEM, Adams, and Mark. This is valuable because it allows users to simulate misuse scenarios or accidents. For example, an excavator, when loading granular materials, may hit an obstacle, and the simulation can be used to determine any potential damage using Mark. With the ACSI link-ups defined and the communication channels open, the user can then proceed to simulating their equipment. During simulation, both EDEM and Adams are running simultaneously with a constant transfer of force and position data between them. I'd now like to just show you a couple of examples of the coupling in action, starting with an excavator. In this example, I want to show you how the Adams-EDEM coupling can be used to evaluate the performance of a bucket excavator during a digging cycle. In this example, the bucket motion is controlled entirely by Adams, and there are four distinct phases: the initial dig, the lifting up from the bed, rotation, and then the subsequent dumping of the material out of the bucket. To help demonstrate the importance of including EDEM in such simulations, we'll be comparing the performance of the excavator as it operates in different material types. So in this video, we're looking at those different materials and how they influence the force acting on the bucket, the mass of the material moved, and also spillage. First, we see the bucket going through a coal material, and you can see the forces in the top left that are acting on the bucket over time. When we compare those forces to two different materials, first an iron ore, a much heavier product that results in greater force, and then secondly also a limestone, which is slightly lighter, however, because of the cohesion, it has a greater resistance to being dug out. With EDEM, we're also able to investigate how much material is retained in the bucket during the digging process. The spillage is identified as a change in mass in the bucket during the rotation of the boom arm, and then the discharge rate is captured during the unloading phase. I'll just let this video play through one more time so you can take a look at what's taking place. So here we can see the forces rising during that digging phase between 0 and 6 seconds. The force remains pretty constant during rotation, and then finally it levels reduce it to zero as materials unload. And you can see the variation you're getting with the different materials. Again, here we're using one of the EDEM's capabilities called virtual bins. This is basically measuring the mass within that bucket over time. In this next example, we're again comparing the effect of different material types. And this time we're looking at a skid steer loader digging into an unconstrained pile of materials. So the previous example showed a bed of material that was constrained on the sides. This time the pile is free to move and react much more freely in response to the equipment dynamics. The two materials we're simulating here are gravel and wood chips, and you can see how the skid steer assembly reacts to the material piles as it passes into them. I'll just let this rewind back to the start and you can see. In particular, right at the start when the materials first, or the bucket first enters the pile, we're getting a loss of traction of the wheels. As the wheels then dig in, you get a response from the material pile. In particular, wood chips, which are much lighter than the gravel, show very complex behavior and much more greater spreading of the overall pile, which is really a phenomenon that's very difficult, if not impossible, to predict accurately using hand calculations, and can only be predicted with the accuracy of EDEM. This next example comes from VR Steel, who are based in South Africa. Now, as I said, VR Steel design and manufacture a range of large and heavy-duty mining products. Amongst their portfolio are devices called dragline buckets. Now, these draglines are used in the mining industry to remove large quantities of material or mined product during open cast mining operations. And these things are huge. If you look at the image on the bottom right, there's a man stood in front of one of VR Steel's draglines, and you can see they're not very far off the size of a house. As a result of this size, they're very expensive to build, and optimizing performance and productivity is vital to VR Steel and their customers. Their draglines need to be able to operate in a wide range of material types and mining conditions around the globe. And in the example I'm going to show you, VR Steel needed to develop a new optimized bucket design and wanted to streamline their design process to ensure that their customers received a design solution that was assured to fill easily and empty completely, operate at maximum capacity, have increased wear protection, and reduce operating costs and improve overall efficiency. In order to achieve their goals, VR Steel made use of EDEM and Adams in order to assess potential design. In the video shown here, we're seeing a comparison of two of their designs. The one on the top is VR Steel's Generation 1 bucket, and the one in white on the bottom is their new second generation bucket that they developed using the cosimulation method. By using EDEM and Adams, VR Steel were able to simulate realistic equipment motion for both the soil dynamics and the dynamics of the bucket and lifting gear. This co-simulation allowed the complete digging cycle of a dragline bucket and chains to be simulated, and virtual performance testing predicting the prototype bucket, including metrics such as the mode and rate of pull, transient loading of the bucket and the gear, wear patterns, and rates. So the two graphs on the right show you some data from their analysis. So the top right graph is looking at the forces that are acting on the chains during the course of the dragline's digging cycle. What you can see is as you get to the end of that time, the lines stay very similar. You're seeing an increase in the in white rope forces, but purely because it's digging more material, which you can see from the mass in the bucket graph that's on the bottom right. By assessing this data that would otherwise not be so readily available, Steel were able to optimize their bucket and their dragline bucket to provide the best filling characteristics whilst minimizing the drag force. Now, this allowed VR Steel to realize a number of benefits, including they were able to perform repetitive testing under the same operating conditions and converge more quickly to the best design. It allowed increased fill levels of their bucket, which meant more dirt could be shifted in a single drag operation. It reduced the filling cycle, so this allowed more drags to be completed per day. And by reducing the bucket mass, this resulted in overall energy efficiency saving for the whole process. Furthermore, because they were able to do so much of the design in the virtual environment, it meant that they only had to use one physical prototype, which obviously saved a large amount of time and money. Their clients also benefited. From this new design, the operating cost was resulted in an overall productivity gain of 2%, which is a significant saving on a piece of kit of this size. The next example is a mini excavator that is trying to make its way over a gap. In order to traverse the obstacle, it first needs to fill the hole with material. On the left, you can see the material being pushed by the mini excavator, and they're colored according to their height. The graphic on the right displays the force acting on the blade at the front of the mini excavator in the X direction, as well as the amount of material that's inside the pit, again measured using one of the virtual sensors that are available in EDEM. As you can see, in this particular example, we're simulating the behavior of a tracked vehicle. So here, the actual tracks of the vehicle itself are made up of a large number of individual parts. Each of these individual linkages of the track are modeled in Adams and are able to react independently to the material model as it drives over it. As with the tracked vehicle, the Adams-EDEM coupling is opening up possibilities for more accurate investigation of complex vehicle ground behavior. So in this example here, we're showing an all-terrain vehicle that's traveling over a bed of soft soil. All the parts of the system have been linked between the codes. That means that the behavior and inertia of the all-terrain vehicle as it goes down the hill are taken into consideration. And this in turn also will then influence the soil behavior as well. The interaction between the codes is much more clearly shown in this example here. The ATV is on a flatter soil surface, but is faced with an obstacle. As the vehicle first comes into contact with the pile of dirt in the middle of the flat plane, it's slowed down and the back wheels begin to slip. Once traction is re-established with the ground, the vehicle is then able to drive over and knock through the obstacle and continue on its path. The examples shown are just a few where the co-simulation approach brings benefits. By combining Adams and EDEM, a wide range of equipment manufactured across different industries can benefit from the increased accuracy provided by the co-simulation in the design of their heavy equipment. So key sectors include the construction industry, where earth-moving equipment such as wheel loaders, excavators, backhoes, and bulldozers can be designed. In mining equipment, we've seen the case of the dragline, but also things like truck bodies or even underground applications such as lawnmower shearers all have potential. In agriculture, managing the equipment-soil interactions is often critical to the success of a piece of equipment design. And specialist equipment such as plows or harvesters that need to handle a range of organic bulk materials will benefit from the co-simulation method. Or, as we saw in the final two examples, There are also applications in the vehicle ground sector. So whether this is off-highway or even military vehicles, when these vehicles need to operate in rough terrain, combining EDEM with Adams allows engineers to really assess how that equipment is going to perform, whether they're wheeled or tracked. So, to summarize, by combining the leading simulation tools of Adams and EDEM, engineers have the opportunity to gain new insight into their heavy equipment design. The realistic material loads of EDEM combine with the systems dynamics of Adams to give increased accuracy and allows engineers to perform extensive what-if analysis without the need to build large numbers of expensive prototypes. The coupling with Adams provides new insights into equipment and material interactions, allowing for optimized equipment design, reduced physical testing, reduced time to market, and improved overall design quality. Thank you very much for listening. If you'd like to know more about the co-simulation method between Adams and EDEM, then please contact either myself or Ejin, and we'd be very happy to talk to you. If you want to know more about EDEM simulation, then please feel free to visit our website on www.edemsimulation.com. And now I would like to hand you back to Ejin, and I would welcome any questions that you may have. Thank you very much.